audience. Thank you all so much for joining today's seminar on quantum-enabled technologies and their potential impact on future conflict and warfighting. This webinar is part of our program's work here at the Institute on Future Conflict, which I'm humbly leading within our small team at IISS. And just a quick note here about the work we do. Our focus within the program, or rather within the future conflict arm of our program, is on the crossover or integration of cyber, cognitive space, and classic kinetic operations. In other words, we seek answers how to effectively integrate different warfighting dimensions or domains and what its implications are for military power and future warfighting. Of course, we are particularly trying to pay close attention to advanced technologies, but we are also trying to avoid technological determinism in our analysis, because human doctrinal and organizational factors can be as important in determining military effectiveness. So when we look at quantum-enabled technologies today, we are trying to stay clear of any hype surrounding their potential military applications in warfare, and really simply try to lay out the facts here. Quantum-enabled technologies have certainly come up time and again as potentially disruptive technologies over the last couple of years that can revolutionize warfare. And I think we need to pay close attention to what is really happening at the technical level here. For example, just recently, during our Defense Innovation Talk series back in March, the chief of the British Defense Staff, General Sir Nick Carter, noted that quantum computing was both his biggest fear and hope, which I thought was a really interesting statement. And perhaps we can also talk about this later during our discussion. In any case, in today's seminar, Dr. Michal Krelina has kindly agreed to give an overview of the military potential of quantum technologies, drawing on his article, Quantum Warfare, Definitions, Overview, and Challenges. It's really an excellent piece. You can find a link to it on our events page. If you haven't read it yet, it's really thought-provoking, and I think it will really trigger debate on the subject for some time to come. Dr. Krelina has a PhD in experimental nuclear physics from the Czech Technical University, or CTU, in Prague. He previously held a postdoctoral position at one of Chile's most preeminent technical universities, after which he returned to CTU as a research scientist. Currently, he's a visiting scientist at Heidelberg University, and he's also founder, principal researcher, and consultant at Quantum Phi in Prague. His areas of interest are theoretical high-energy particles and nuclear physics, and quantum technologies, with an emphasis on applications for defense, space, as well as the security sector, and quantum technology risk and threat assessment. We're really glad to have him here, and I'm really looking forward to a great discussion. Our second discussant will be Dr. Greg Austin, my colleague, who leads the Cyberspace and Future Conflict program and is based in our Singapore office. Prior to joining the Institute, Greg worked at the University of New South Wales, Canberra, as a professor and deputy director of its multidisciplinary Center for Cybersecurity Research. He's the author of a number of books on China and cyber issues, and has also been the editor of a number of cyber-related volumes about China. Greg has held senior posts at the East-West Institute and the International Crisis Group. He was a senior research fellow, a visiting fellow in the Department of War Studies at King's College London, director of research at the Foreign Policy Center, and he has also held various academic posts at the Australian National University, where he also studied for his PhD. So we're going to kick off our discussion with a presentation by Michal, followed by Greg, who will provide an overview of the challenges governments will face in adopting quantum-enabled technologies to military use. Following Michal's and Greg's remarks, we will open it up to Q&A. And I would really prefer if you type your questions into the chat functions that you can find on your Zoom interface. That would be greatly appreciated. And we have plenty of time for a good discussion, I think, over the next 90 minutes. So again, thank you very much for joining us today. And without further ado, let me hand over to Michal for his presentation. Michal, the floor is yours.
Hello, good morning or good afternoon. So let me start to share the slide. So first of all, I would like to thank to organizers for this opportunity to speak here. It's really honest. So I would like to speak about the possible impact of quantum technologies for military application. And there is some outline. Big part, first part where I will provide some overview, but a very fast overview of all possible military applications. Actually, I could speak plenty of time about that, but we have about only 30 minutes, so just a very fast overview. And then I will try to see this topic from more top. And I will mention some term of quantum warfare, possible scenarios. Also, very important topic is how much all is real or hype. Then I would like to mention some terms like quantum awareness and R&D. Since I will not have time to really go in details, I can recommend my papers where I really map all possible what I found military application of quantum technologies, including a description about the time expectations, probability, and what the state of the art right now. Okay, so first slide is a little about the physics, but I really don't want to speak too much about physics, so there are only some terms that you should know that are connected with quantum technologies, like no cloning theorem, entanglement, superposition, energy levels, coherence. If I will speak now about quantum technologies, we speak about something we call the second quantum revolution. So it means that there was the first quantum revolution that refers like about 100 years ago when the foundation of the quantum mechanics was discovered and described, and then there were first applications like nuclear weapon, nuclear energetic, imaging system in the hospital, lasers, semiconductors, and so on. But there we work with at the, let's say, atom level, at the quantum mechanical level, more statistically. But now in the second quantum revolution, we work with the individual quanta. It means directly electron, ion, atoms, or artificial atom. That allow us to reach some fundamental limits of quantum mechanics and provide us some new capabilities, like up to exponential speed up of computing, really secure unbreakable communication, or a very precise measurement of various physical quantities. And the last term that it's good to have in the mind is quantum bit, or shortly qubit, is the quantum analog of the classical bit. Classical bit can be 1 or 0. Quantum bit can be 1 and 0 as well, as some superposition of both values. Actually, it can be complex superposition, so there are many options. The disadvantage, especially in the terms of quantum computing, is that they cannot be copied. So it has very deep consequences for security, actually a very big advantage. But because the quantum bits are unstable, and basically the coherence or lifetime of the qubit is pretty short, but for the calculation we need it live longer. So we need to apply some correction mechanism. And you can imagine if you cannot copy it, that these correction mechanisms are much more difficult. So first overview is about quantum computer. Since I don't have time to really go every point, so I will mostly speak about the status and possible military application. So in case of quantum computer, so approximately the best universal quantum computer available is with 65 qubits. In case of quantum annealer, that is not universal, it has more limitation, is about 5,000 qubits. And for example, the expectation of IBM or Google is to have like 1 million of physical qubits in 10 years. I speak about physical qubits, so it's individual electron or atom. But then we have term of logical qubit. Logical qubit is supposed to be something like perfect or nearly perfect qubit that will consist of many of these physical qubits and some error correction code. So in general expectation, some really useful quantum computer is expected like in 20, 30 years. So about the application, so a priori, the quantum computing was recommended, and the basic idea is because for the simulation of other quantum systems that are not so easily accessible. So for example, all chemistry is such an example. So there are many startups about how to apply the quantum simulations of chemistry for example, for new drug discoveries. From our point of view, we can ask how large could the impact, for example, for CBRN defense, if it can help for discovering new detection methods, or it can help to, let's say, design new chemical warfare agents. But especially this topic really need to have more assessment. That is actually one of the projects I'm working right now on. The same principle you can also apply for the new material design, for example, better camouflage, better stealth, high temperature tolerance material, high temperature superconductivity, and so on. The other big topic is cryptanalysis. It means, for example, the short breaking RSA algorithms, but it's not only short, and it's not only RSA encryptions. So it's a pretty big topic in cyber domain. The other big area is the quantum optimization. So a priori, it refers to the problems of the NP difficulty. So are very difficult problems that we don't have exact solution. Usually we have some heuristic solutions. So it means we have some approximate solution. And with the quantum optimization, we can have even better approximate solution. So you can, there are many use cases for logistic, but in our case, we can use for planning, missions, war games, system validation, and so on. And the last big topic is enhanced military AI and machine learning. And basically, you have two types of quantum AI. First is full quantum AI, but it refers to process of the directly quantum data. But if you want to use classical AI, for example, for picture, text, whatever, so you can use all quantum machinery for improve the AI machinery inside. So basically, everywhere where you today use or you plan to use AI in the future, possibly with a better quantum computer, you can improve it. Okay, so the large topic is quantum communication. Quantum communication a priori refer to exchange of quantum bits between two nodes at some distance. First, I would like to note we have two types of the quantum networks. First, what is actually today is commercially available is the, let's say, simplified quantum network for quantum key distribution. So this type of network has only one function, only for the distribution of the key. The reason is that for this feature, we don't need quantum entanglement. But for many other functions, we need quantum entanglement, and that require quantum memory. And unfortunately, so far, we don't have some really reliable quantum memory. Also, what we are able to accept the connection through the optical fiber. There are pretty famous experiments, especially from China, about the communication between satellites and ground, and very recently, for example, between drones and ground. And except the quantum key distribution, you can directly, you can use the same very secure channel. But about the security, a priori, you can prove that this channel, if you will build it correctly, you cannot hack. If someone try to read that quantum data, you will recognize. But of course, it's not completely perfect system as the complete, because the both and nodes are still combination of quantum technology and the control system is classical. So those end nodes will be the weak points in the future. There are other some interesting functions, for example, identification without revealing authentication credentials. So for example, who try to follow you, he will not see login and don't know who is connecting. Position-based cryptography, for example, you will accept only messages from, let's say, from some command center. A very important part and more technical part is the distribution of precise time. That's important for many quantum applications as well. You can use it for the classical system, for example, for classical radar or electronic warfare systems, and of course, navigation. Other interesting things is, for example, self-organization. Imagine, for example, a swarm of 20 drones, and let's say you don't have any leading drones, and all drones are at the same level. And they need to somehow agree who will do what. Someone will observe, someone will attack, for simplicity. And in classical algorithms, the complexity of this agreement is increasing with number of elements. In the case of the quantum algorithms, or especially applied in quantum network, it's linear. It doesn't depend on the number of the elements. Okay, shortly about random number generation. So quantum computers or special embedded systems for generation of quantum random number generation can provide you truly random number generation. It's important, especially for security application, for example, for key generation, for QKD or classical cryptography. And what is significant advantage, you can certify that it's really random, and you can verify it's really random. So far, we use mostly something we call quasi-random number generation. Big topic, also mostly in a cyber domain, is post-quantum cryptography. Actually, it's nothing quantum, are basically only classical algorithms that are considered enough difficult even for quantum computer. But basically, you cannot mathematically prove it. So it's let's say some small risk that in the future someone very smart will discover some quantum algorithm that will exploit some hidden symmetry of one of this algorithm, and this algorithm will be broken. Okay, the other big part is quantum sensing. Again, we have many different platforms, many different physical principles how to do some measurements. Most of them are basically as laboratory prototypes, including tested outside or even in the space. So basically, it is able to measure all basic physical quantities like magnetic and electric field, inertial forces, including gravity, rotation, and time. So all possible military application could be, for example, quantum inertial navigation that is expected to be like 100 times, at least 100 times more precise than the current inertial navigation. There are other more exotic non-GNSS navigation, for example, based on the Earth's magnetic anomalies. There is expected plenty of small improvement with application in general for ISTAR, for example, underground surveillance, undersea exploration, mines, EID detections, and so on. Very interesting topic I will speak a little bit more about later is quantum antenna, especially for electronic warfare. Next, for example, improve radio frequency spectrum analyzer or better chemical detection. Okay, other part is quantum imaging, and part of quantum imaging is also famous quantum radar. So in this case, we work with the photons. Typically, we have some source of photon that we send somewhere, and we will we are waiting when it's returned. There are various protocols how you can provide that experiment. Also, all is at the laboratory level. And what can bring you, for example, 3D cameras behind the corner camera, and will allow you to see in a much more difficult condition, like in all weather, in the night, at different frequencies. And also there are a little bit, it's more exotic, but quantum analogy of the, for example, GPS. In case of quantum radar, that's things with pretty much hype. Theoretically, in laboratory, those principles are mostly verified at the laboratory level, including for microwave regime. In theory, it offers some better signal to noise ratio. These quantum radars should be invisible itself, so we can speak itself. That the big problem of classical radar, they are very easily visible by electronic warfare systems. And some of the protocols offer target illumination. So it means that you can identify the target. However, here is a very huge problem with the microwave sector that makes very improbable, unlikely that we will have something like long-range surveillance radar. So more probable is the quantum radar. It uses the optical or around the optical wavelength for the photons, and for example, for a space application or very short distances. Okay, the last from this first part is the quantum clock. So it refers to very precise measurement of the time. It's very important because, for example, for quantum imaging, you really need to record every detection of the photon. So you need very as precise as possible the timing. So and the same apply for the GPS, for quantum sensing. Even if you do classical radar or classical electron warfare, you will provide more precise timing. They can work even better. So we can speak something like quantum enhanced radar or quantum enhanced electronic warfare. So if we will put all together, so we can have like quite a quantum picture of the possible future warfare. So quantum warfare, in these terms, it's not only, of course, the basic is the military application of quantum technology. That is important. It will affect all of the domain of warfare. So air, navy, army, space, cyber, but also intelligence, in general security. And in general, this quantum technology will bring you better efficiency, new capabilities. So probably you will want to improve some strategies and tactics. For that, you will need new doctrines and some simulation scenarios to know what to expect. And in general, every military technology that will give you some advance is also some theoretical problem. There can be consequences for international security and peace. There are some ethical questions that I will mention a little bit later. The other big topic that is very close connected is quantum workforce. If you want to have own R&D or just monitor quantum technologies and their improvement, you need people who will understand it. And these people will not appear just like this. So you need some education. This is a pretty big topic, especially in the United States, where they consider even some basic of quantum information science, even at the high schools. And the minimum what you should do is some monitor and awareness about the quantum technologies if you don't have your own R&D. Okay, so can we speak about something like quantum weapon? No, this the second quantum revolution is not coming with some fundamental new weapon like in the first quantum revolution. It was the nuclear bomb. It's rather it will improve the sensitivity, efficiency, or introduce new capabilities of the current technologies, not necessarily of weapons, but also of weapons, and some supporting system all around. And what can be quite exciting, but at the same time also scary, if you will combine various quantum technologies at one platform. I have one graphics, for example, you can imagine in long-term future drone that will communicate through the quantum network that is pretty secure, that will be connected to C4 I-star, complete. Then the navigation will be with just quantum enhanced GNSS. In case it will be jammed, it will have own inertial navigation, and it can have plenty of the quantum or quantum enhanced sensing, like underground mapping, electronic warfare receiver, the quantum imaging, or chemical detections. So there is one, I choose like two big areas in the military where I will expect a very big impact. So one of the is cyber domain. Here we have quantum computing, especially in the terms of crypto analysis. So the attack against the public key encryption or message authentication code. And theoretically, it can make weaker the symmetric key encryptions, but it will cause very huge quantum computer resources that we cannot expect in next decades. And other things, as I spoke before, is enhance AI or machine learning, especially for automating cyber operation. Again, the quantum computing is mostly post-quantum cryptography, so our classical algorithm, but with basically enough difficult problem even for quantum computer. But as I said, we cannot exclude that someone will discover some better algorithm that will break some of this algorithm. So the technically more difficult way, but more secure, is to use the quantum communication in the form of the quantum key distribution or direct communication, and so on. For both post-quantum cryptography or quantum communication, you need a quantum random number generator. And the other part is what is called C4 I-star. It refers to command, control, communication, computer intelligence, surveillance, target acquisition, and reconnaissance. So here again, especially at the command and processing part is quantum computing. So with the enhanced AI or machine learning, you can enhance the, let's say, the target recognition. You will generate better picture of situation awareness. You can apply optimization for mission logistic. And in case when your quantum sensor will produce quantum data, you can apply, of course, directly quantum data processing. When you have, then you have some connection between, let's say, command part and detectors and soldiers. So you have some communications. So that apply basically the same as the previous slide. And then you have the sensor part. So it's quantum imaging, it's radar, lidar, 3D cameras, quantum sensing, quantum antenna, underground mapping, mine detections, submarine detections, camouflage vehicle and aircraft detections. And all really, especially when you have many data and all is faster and faster, you need a precise timing and time synchronization. So, and it's the best with quantum clocks and synchronization using the quantum network. Here I would like to highlight especially the C2 system, the command and control. Unless you have some really new groundbreaking weapon, like was the nuclear bomb in the Second World War, the most probably you will win the battle or war mostly because of good command and control. So from the more simple view, it consists of two parts. It's a situational awareness that make the picture of the current state of the battlefield from the sensors, from the soldier reports, from intelligence. And the other important part is some simulation of scenarios. Something you have prepared, some things you do, some simulation you do in parallel, and based on these two parts, you do some decision. Decision makers need to do some decision. Actually, this is pretty big topic right now in combination with AI, because AI make this many things easier, like the target recognition on the picture from satellites, and it's possible to process many data and show you only those most relevant. And also at the simulation side, it can provide you high fidelity simulation. So it's leading to faster and more qualitative decision, and that will help you at the battlefield to win the possible battle or war. And now you can imagine what will happen if we will have, for example, especially the quantum computer with the quantum enhanced AI and optimization. So you can process all even faster with bigger amount, and including, and especially with the quantum optimization, you can do even much more complex simulation with more variables and more uncertain, unknown variables. Okay, so now, but maybe many of you can ask, is it all real, or just hype? It's just a fantasy of some scientific geeks? In the quantum jargons, I would answer it's a superposition of yes and no. Many of the technologies I introduce you today are mostly verified at the laboratory level. So it's basically working, but very big question and unknown is the transition from the laboratory to some product, and at the end to battlefield deployment. That is a very complex process, because typically in laboratory it needs cooling to close to absolute zero. It's huge, it's heavy, it's expensive, and still not perfect. And all this you need to improve. You need portability, sensitive. In a laboratory, it's very sensitive with good resolution. But if you want to keep the same sensitivity and resolution, for example, for underground mapping, if will work from the satellites or only from UAV, or you need to only from some vehicle, that's a big uncertainty that we cannot answer right now, at least unless there is some confidential research where they are more advanced. And of course, you will require small size, weight, power, and of course the cost. And there are more uncertainties. For example, all my research, what I present, is based only on public domain research and information. It's known that very advanced armies or countries, for example, United States, China, or UK, there the individual parts of army, they have own laboratories, and there they have dedicated departments for quantum research. Other big source of uncertainty is something like a hype, especially from quantum industry, because the quantum ecosystem, quantum industry is a pretty rapidly growing area, and in the future, especially they create the products they will sell in the future, but they need investment, so they can a little bit overhype what all will be possible in the future. Also, sometimes you can see that scientists who do some interesting, maybe groundbreaking research, basic research, so they foresee some application in the future. But as I said, the transition can be very, very complex. And to be more messy or more uncertain, there is something I call state propaganda, especially from the China, where some of their statements, for example, about quantum radar, seems very, very strong. So I prepared two examples where I particularly myself see some typical example of what is realistic and what is unrealistic. So what is unreal is quantum radar, at least in the sense of the microwave regime, long-term surveillance radar. So unfortunately, there is quite big hype, especially created like 2 years ago by several articles from China, but also from Canada. in many of these newspaper articles, you can see misunderstanding of the principle by writers that also will not help much. But yes, as I said, it's verified in the laboratory. Actually, one interesting point is that for many years, we believe that quantum radar cross-sections is better from quantum radar, but it was disproved. It was only just some of minor mistake errors that will create something, some hope about better radar cross-section, but it was disproved last year. And as I said, there is a huge challenge in the microwave regime. So with the current technology we have, it will be, if you will want to build a quantum radar, it will be extremely impractical design, huge, and extremely expensive. But I mean extremely, extremely expensive. At least what expected or what some expectation is done by Raytheon company that is working with classical radars. So the most probably is something like in optical regime, so it means lidar. At the other side, what is not pretty common in the newspaper articles is something we can call quantum antenna. It's technology based on the Rydberg atoms. The advantage is that it can have a size of few micrometers, and it can measure all frequencies of all radio frequencies at all wavelengths, including amplitude modulations or frequency modulation. It's a very interesting improvement for electronic warfare, because so far, if you want to detect some radio signal, the size of your antenna need to be like at least 1/3 of the wavelength. But in this technology, it's independent of the wavelength. So if you can detect even signal with very, very long wavelengths, and you don't need to have 10 meters long antenna. So far, this advantage is you need some cooling, but a recent advantage, for example, demonstrate the possibility of measurement of if you will have two small cells a little bit far from each other from the phase difference, you can estimate the angle of arrival of the signal. So we can imagine in the, I would say, like close to midterm future, something like IISS module. IISS module, it means you can have some matrix of small quantum antennas where every 3 modules will detect one signal and estimate the direction, and other cluster can detect other frequencies and so on. And it's recently pretty large interest in R&D of this technology. So I'm almost finishing. So last 2 slides is about what you can do now. Basically, as I said, we cannot say for sure what, when, and how will be successful, and we will be able to deploy at the battlefield. So at the minimum, what we should do, at least, for example, smaller countries where they don't have much military R&D, is to keep awareness, to keep monitor quantum technologies, to see what is the state of the art, how successful is the transition from the laboratory to some particular product, especially with the possible military application. And of course, the better, and many countries even did it to start their own quantum R&D. So of course there is a higher, but possible higher gain. And when it will really come, you will have the advantage. You can see, for example, in financial sectors, that in general, many banks, huge banks, starting to be seriously really look in this quantum R&D. So to keep these 2 points in the mind is some kind of, I would call it quantum insurance. Actually, it's not from my mind. I think it's from the head of IBM or someone like that. So to at least to keep some knowledge and better to work on it. And especially in case of, for example, C2 system about command and control, probably you don't want to buy some other system, especially in the future when the AI will be included. It will be very difficult to do some audit and verification. So it's better to have some national resources for to build and implement such system, for example, for C2 or intelligence. Okay, the last few notes about the ethics, risk, and control. So in general, improvement of weapons can make the higher international tensions and more risk of some conflict. But as I said, basically there are no new weapons. Even now are more discussion about controls and exports about quantum technologies. For example, China bans export all cryptography systems, including quantum. In the European Union, they discussed that in the research in the Horizon, that is like a big platform for platform is big package of the money for research. They will exclude countries outside the European Union and so on. And in case of the ethic, because most of the quantum technologies improve some particular system, for example, AI, for example, inertial navigation for a hypersonic missile. So I would expect most of the ethic discussion within individual technologies. So conclusions, quantum technology seems to be very promising and interesting improvement for military system. However, it's very unsure. We cannot say with to be sure what all will be successful, what we will have in the future. However, it will be very dangerous not to completely ignore. It's the similar story as for AI, where you cannot also afford to ignore it. So the minimum what you should do, especially in the case of smaller countries, for example, in my case, I'm from Czech Republic, so we don't have, our army doesn't have much possibilities about the R&D. So at least to have some monitor and to keep some quantum awareness. And if you afford, you should work on your R&D, especially for very sensitive systems. Okay, so just a little bit for fun. This sketch became a little bit viral at Twitter with some people, of course, yes, he's a fan, and you put quantum in front of everything. So yes, now it's mostly like fun, it's just for fun. But in the future, I'm not so sure it will be so fun. Okay, thank you for your listening.
Well, thank you very, very much for an excellent and insightful discussion, Michal. And I have to say, I'm partially to blame for this particular tweet going a bit viral, just because I tweeted it out and I've had no ill intention behind it. I just wanted to trigger a discussion, but it was interesting, some of the responses, and some of the responses were actually quite thoughtful. I definitely also learned from it. But yes, excellent discussion. And very, very impressive. And I think there's plenty to go with over the next 40 minutes. So I don't want to waste any more time with my remarks and just hand it over to Greg now for his part of the talk. Greg, the floor is yours. Thank you.
Well, thanks, Franz, and thank you, Michal, for an excellent presentation. Ladies and gentlemen, thanks again for joining us. We'll say at the outset, if it doesn't become obvious in the first 2 or 3 sentences, I'm not a nuclear physicist, I'm a political scientist. And what I want to talk about are really something about the pathways by which new technologies see it make their way to the field in military applications. Michal used the term second quantum revolution. And I think that's an interesting framing point. We could put that down to hype, but I think that we should accept, in a sense, the way in which governments have acted in response to the opportunities presented by quantum information science. We can take that as a measure of whether there is a second quantum revolution or not. And I think that the sort of language, and in the sense that the importance of what's underway that's evoked by the term second quantum revolution, I think is worth taking on board. We can get some sort of sense of how cognitively dissonant this sort of research is So when I was researching a book on China's cyber policy, and I read that Chinese scientists in 2012 had successfully achieved the teleportation of the electronic properties of remote subatomic particles. It took me quite a time to understand what that might mean, a little bit of research. And of course, China has forged ahead in quantum communications research and in their ambitions to implement a quantum communications system. But you don't have to look very far to find a high level of excitement and serious commitment from governments to quantum information science and its potential applications. So US government, for example, published a report using the term quantum superiority. The UK government the US government used the term quantum supremacy. The UK government used the term quantum superiority. And in both cases, I think it's supposed to mean that point in time where quantum computing replaces or classic computing. I guess the qubit takes over from the classical bits. Let Michal explain that more perhaps. But there's no mistaking the potential military applications of this science as Michal has outlined it. To put it in layman's terms, one of the phrases I encountered was that quantum science may allow us to see around corners, map hidden underground hazards, and easily solve problems that would stump any existing supercomputer. So most people on the call probably already appreciate that. But I thought it was just worth putting out there in the first instance. So if we look at what the Defense Advanced Research Projects Agency in the United States is doing, DARPA, we can see that they've got 10 unclassified projects relying on technologies of the second quantum revolution. And they include projects for enhanced imaging, as Michal mentioned, and enhanced atomic clocks. Enhanced atomic clocks have all sorts of important military applications. If you read some of the material on the DARPA website, you get a feeling that it may be one of the areas of the technology, and again, I'll let Michal comment, and others that might emerge in applications sooner rather than later. Just to give people a little bit of stimulation from bibliometric comparisons of the sort we've seen around AI, I had a look to see what the Web of Science database is saying about which countries are doing what in terms of the best research on quantum information science. And if we just restrict ourselves to the field of quantum enhanced imaging, the Web of Science database for 2011 to 2021 shows that China is the leading producer of the most highly cited open source papers with 260. The US has 197, Germany 63, and Singapore 45. And while we might note with interest the achievements of China and the United States, I think something about quantum information science, which has Germany in third place and Singapore in fourth place, is a very interesting development. And in a sense, an indicator of how we should enhance what Michal is calling our quantum awareness. One interesting element of those statistics on scientific papers, especially with regard to enhanced imaging, is that some of them have very plainly civil sector applications. So for example, many of the Chinese papers relate to enhanced imaging for agriculture rather than for military applications. But nevertheless, the DARPA projects on enhanced imaging demonstrate the high military relevance of the underlying technology. Quite interestingly, if you look at who funded the papers in the United States, two of the biggest funders are the Departments of Defense and the Department of Energy. Of course, we all know the US Department of Energy is responsible for the nuclear weapons that the United States has. Quite interestingly, the funding from US government agencies went to public US universities, where in many cases Chinese scientists have participated in the research. And my footnote to that is that open source science is globally available, and the US has equal access to Chinese open source research. And in fact, one remarkable thing about all of the articles that are highly cited in the information I gave before are all published in English, every single one of them. Okay, just like to echo a couple of points from Michal's paper, which I think are quite interesting. He does suggest that quantum technologies will be so widespread and so transformational that they will impose new demands on military strategy, tactics, and doctrine. I think that's important for our quantum awareness. And quite wisely, Michal does not offer a time frame for when those technologies might mature. But one of the interesting and perhaps troubling developments to watch for is that states may already be collecting and simply storing highly encrypted secret documents of their adversaries, waiting for future quantum-based technologies to help decipher them. Michal also mentions undersea warfare, which I think is an interesting area to contemplate in terms of possible highly transformational achievements for military applications. I could also mention that in the US Secretary of Defense, Lloyd Austin, in his confirmation hearings on the 19th of January, identified quantum computing as the first of 4 areas where the United States would need to make advances if it wanted to keep a military edge over China. The other 3 were artificial intelligence, the advent of connected battlefields, and space-based platforms. For its part, we know where China is headed in broad terms. It has announced its intention to have a fully functioning global quantum communication system by 2030. At a Politburo study session on October the 20th, President Xi Jinping singled out quantum technologies as the vanguard of a new round of sci-tech and industrial revolution. He called for stronger policy support, more investment, training of more researchers, and giving scientists more autonomy in this field of research. So there we are, Xi Jinping at a Politburo study session, quite notable. The emerging technologies will severely test the limits of available human resources and national investment plans in the few major powers that can afford them. So Michal made some observations about the capabilities of the Czech Republic, but clearly, as Xi Jinping's statement alluded to, the training of more researchers is going to be a fundamental part of the advances that any country can make in quantum information sciences. Now, I'd like to just talk you through a few anecdotal type things from history with a couple of observations, but to do that, I'd like to put up some background judgments that I've made about what's the likely direction of the adoption of quantum technologies might be. And I'll let you take them on board rather than walk you through them. But clearly, I'm staking a lot on the possibility of technological surprise in the field of intelligence, surveillance, and reconnaissance. We might return to the points on the slide a little bit later. I don't have much more to say, but I just want to walk you through a few historical precedents about the pace at which new technologies can move into application. If we go back to the Manhattan Project, the first quantum revolution, and while it looks like in broad terms it took about 4 years for the Manhattan Project to go from the commencement of the project to the dropping of the first atomic bomb, the first major breakthrough was actually made within 1 year of the project starting, and that was a successful test of a nuclear reactor. and much of the subsequent time was spent producing the plutonium and the enrichment of uranium for the bombs. So within 1 year of the Manhattan Project starting, probably the most significant scientific breakthrough that was needed and practical breakthrough that was needed had already occurred. So that's within 1 year. And we should bear in mind that that was at a time when scientists did not have access to advanced computer-based simulation for development of those sorts of weapons and technologies. Similarly, if we look at the Ultra project in the UK in World War II, we went really from 1939 to 1940 through to 1945 with a major breakthrough almost every single year. So without studying Project Ultra in great detail, we might think of the name Alan Turing, and we might have this image in our mind of the movie that was made about him, where he more or less led most things that resulted finally in the production of the computer that kicked off computing science in the way we might know it today. But in fact, there were others in that project who made important breakthroughs after Turing. And Turing, perhaps his most important breakthrough probably was 1940, if I've got my date right. But then Tutt, Flowers were involved in production or design of important computing machines through the war that really brought about or contributed greatly to the Allied success, especially the British war success. And what I'm really trying to emphasize there is that you can have these big breakthroughs in technology in very short periods of time, especially when smaller numbers of people are involved and you're not looking to roll out the technology to a 200,000 person army, navy, or air force. Radar, which Michael has alluded to, suggesting quantum radar is not going to be necessarily as likely as a quantum antenna. But the history of radar development in World War II is an amazingly rich history of sequential technology breakthroughs, not least, of course, for the purposes of winning the Battle of the Atlantic. And if you read a couple of the histories of radar in World War II, a couple of the researchers and technical historians, technology historians, talk about the complacency of the Germans and the Japanese armed forces in how they approached the development of radar relative to what was going on, especially in the UK. On the other hand, and just to sort of finish off on this sort of anecdotal note, some of you on the call may know about the failure of intelligence in Hawaii in 1941, where a radar station on the north of Oahu detected the incoming Japanese aircraft for the attack on Pearl Harbor, notified a lieutenant who was in charge of the radar detachment, and the lieutenant dismissed it as probably just a returning US bomber. So in a sense, while radar revealed great successes and enjoyed great technological leaps and breakthroughs in World War II, there's this early failure on the US side, which is definitely worth noting. And what that little failure points to is a really important point, which is on the slide, and that is the adoption of revolutionary technology fundamentally depends on culture, acceptance, leadership, and a whole range of social things that really don't have a lot to do with the basic technology. And the lesson that I draw from all of that is that when we're trying to understand and be quantum aware, that in our thinking about it, we should maintain flexibility, avoid complacency, avoid cognitive and motivational bias, and expect that quick breakthroughs are possible. And then I'd just like to finish off on this, this general point that technological surprise in the ICT sector and in ISR capabilities is more likely than in more visible weapons or platforms. And if we're talking about quantum computing and quantum information science, quantum imaging, quantum sensing, I think that we could probably not lose a lot or not risk much if in developing a much greater quantum awareness, we focus that very heavily on its ISR potential and on the intelligence community. You don't have to look very far at the work of the United States Intelligence Advanced Research Projects Agency, IARPA, to understand the significance which the US intelligence community is treating quantum information science. I could sort of point out as a footnote that IARPA is funding Australia's leading quantum research project at the University of Sydney. So the intelligence aspect is the one that I'd like to finish my short remarks on and just really emphasize that an intelligence focus to our quantum awareness would probably be a good thing. Thank you very much, Franz.
Thank you very much indeed, Jack, for a great commentary on Michal's presentation and also some of your own ideas about the impact of emerging technological capabilities on warfighting and to what degree we can expect, or in what fields we can expect them to really have an impact first. And also great historical vignettes, of course, the Battle of Britain, the Battle of the Atlantic, and so forth, and the emergence of radar technologies and other capabilities that helped the Allies win that conflict in the 1940s. So I think I just want to give Michal a chance to respond to what Greg just said, and following that, we have a couple of questions in the queue. So maybe Michal, maybe you can offer some brief comments to what Greg just said. And we do have a fair bit of amount of questions. So hopefully we can get to all of them. I've maybe combine one or two, but I'll be reading them out and just expect a response then. Okay, thank you.
Okay, I basically would agree with all that Greg said, especially only just those expectations. It's very tricky. From some point of view, it looks quite slow, but then come very interesting breakthrough research that make technology easier. For example, for the year 2020, when I really try to follow the research in very detail, there was were like, let's say, 2 works that significantly, their impact will be, they significantly make the smaller the refrigerator for quantum computers or quantum sensing. That's important, especially for quantum sensing, where you want to deploy on the UAV or satellites, you will need to cool down. And for that, you need to really small refrigerator, not to have like 100 kilograms big machine. So, but this type of scientific breakthroughs, it's basically impossible to predict. So basically you need to observe the situation, and in such case you need to react fast if you, for example, in your R&D, and implement this new technology that can significantly shift your research forward. So yes, it can happen that even in case of quantum computers, for example, we have different types of qubits, and one of the something like holy grail is something they call topological qubits, thanks to Majorana particles. Actually, there are several bad news because they disprove some discovery of this particle that was done like 2018. It's a research supported by Microsoft. But anyway, theoretically, if someone will discover and employ this this technology, the topological qubit has much better quality in the sense that it's higher quality. It's not so sensitive for environment. The interaction with other qubit is with higher fidelity. So there can be some discoveries that can make the research faster, and all technologies can be bring, let's say, 5-10 years earlier than we can expect now. But this is very highly uncertain to especially predict this type of the scientific breakthrough that could really accelerate your research. But of course, we cannot exclude, and somehow in our consideration of our R&D plans, we should keep some space that, okay, something completely new that significantly help us, we should react and immediately or fast implement in our system faster than, let's say, the opponent. So that's like more general comment.
All right. Well, thank you very much. Let's perhaps jump to some of the questions from the audience here. I have a question here for you. How easy is it for innovations in basic research and quantum technologies, such as the ones you have outlined, to diffuse?
It's difficult to say. As I said, basically all technologies I mentioned are verified in the laboratories. And it's working. It's nothing like, it's no fantasy, definitely. It's not only dreaming. But probably in many of these technologies, they were not able to transfer in something practical. For example, the underground mapping. For example, right now, they have mapping even from the satellites. It's an experiment by NASA. And the spatial resolution is like 100 kilometers. So it's a huge area. If you want to, for example, map some underground base or some underground missile silo, you need to much smaller resolution. And it's a huge question if we will be able to reach, for example, from satellites or from UAV. And so it's a question if really this idea of using for military application for this mapping for underground facilities will be possible. That so many of this type of research can remain like for study of the Earth itself, like with this huge spatial resolution, you can study the movement of the underwater or lava in the volcanoes and so on. But probably maybe no really some underground facilities. So many of these research finally somehow can be useful, but maybe they will not be useful they will not be enough useful for military application. So that the risk of this diffuse somewhere is possible, of course, that we cannot yeah.
Okay. Thank you. So related to this, there's a follow-up question. What sort of specific industrial and scientific capabilities are needed to make use of these technologies? And which states have the capacity to make use of these?
Well, okay. Basically, you need at the lowest level, you need basic research. That is usually made on the universities or some national institutions. There you need some professors, you need experienced researchers who know quantum mechanics. That's the basic level. Then if they do some basic research, you need some application. And then you need some doctors and engineers who know who have basic quantum knowledge, not necessarily extra deep. And higher level still, for example, in quantum computer, quantum programming is much pretty difficult than classical programming. And the person who want to do some develop some quantum software, that you need to change your mindset that the principles are working there are pretty different. Very probably in the future, quantum computer you will control through some library by classical programming, but at the lower level, you need an expert of all types. For example, for quantum computer, it's only one part, that person who really designed the qubit. You need people who know the electronics, because there need to be control electronics. You have many, for example, in case of superconducting quantum computer, you have many cables, and you have big refrigerators, so you need cryogenic specialists for wiring. The wiring, of course, make worse your cooling down, and so on. So it's a pretty complex. The states who have capacity, so the most known, of course, United States, China, they are most known from media, but of course, basically Canada, very advanced is United Kingdom, Australia, and all in most of European Union, there are programs like Quant-Era and so on. So within that are also many research, mostly the basic research. Also Israel and India are like the most dominant. And in general, there is, as I mentioned, the quantum industry is growing pretty fast, or ecosystem. So the startups are growing also in the countries where the quantum technology research is not so strong. So especially let's say, to create a quantum startup in a quantum computing is not so difficult. You only need to learn how to make programming for quantum computers, and many tools are available for free. For example, the basic quantum processor from IBM are until up to 17 qubits are for free available. For more qubits, you need to be partner. So basically, everyone who has internet and who has a will to learn something can learn that. But of course, to be like user, but to be expert, it's need more education and more support in the education and research in individual countries.
Here's a more specific questions, and you of course touched upon it already in your presentation, but this is very specific about what to expect, or what we can expect in the next 20 years. So what kind of military or quantum enabled military application can we expect in the next 20 years? What do you think are going to be the most likely?
Okay, actually 20 years is quite a long time. So many of the application, especially in the part of the sensing and maybe communication, are very likely. Actually, what is the trend right now, as I mentioned, Greg, and I didn't mention in my presentation, is that what your enemy or can or some, not necessarily enemy, but some, let's say, some group with some interest, they can collect your encrypted data, and in case they collect some data that are supposed to be confidential for, let's say, 50 years, but in quantum computer able to break it will be like in 30 years. So you have problem even right now. So therefore, it's a little pressure to implement that post-quantum cryptography as soon as possible. But also, we need to be not too much hurry, because as I mentioned, I think now it's a former head of the CIA. The worst case will be to do too much in a rush and implement some post-quantum cryptography that has some mistakes, and even with classic computer, they can break it, and it can make more problems than we have now. So right now it's the collecting the information that they can break later with quantum computer. Quantum computer in the next 20 years, maybe there will be some demonstration of really practical quantum advantage, but not really we will not be able, I think we will not be able to utilize full power of the quantum computer as we imagine. More probably, we will have something like quantum hybrid system. They work on it, for example, in UK. Most probably, all, especially for HPC high computing systems, will work like you will send some algorithm, some problem you want to calculate. At the level of operating system, there will be some AI that will analyze your computation and put a part computation for quantum computer, part for CPU, GPU, or FPGA. And this seems like the most effective way for the calculation in the future. Even now, for example, in case of AI and neural networks, the hybrid concept that it's combination of classical AI and quantum, where for quantum you prepare in small pieces, it looks very effective. But so far we have use case and demonstrations, but we cannot say we reach some quantum advantage or some quantum practicality where we would do something faster and better than we are able now with the normal computers. In case of sensors, yes, in 20 years, I believe that many can be even deployed at the battlefield in 20 years. I don't think so much about quantum radar unless there will be some huge groundbreaking discovery. In case of quantum imaging, yes, quantum networks, I would expect quantum memory like in 10 years, so really working. So that's possible, and that means you will need to start to build your infrastructure. Quantum clocks, definitely, and quantum RNG we have right now, so that will be available even very close. It's actually now in the form of cloud, as like the product you can buy, it will be in following years.
Okay, thank you. Here's another question, and Greg, feel free to jump in on this one as well. To what extent has China raced ahead of the US and Europe for exploitation of quantum communications, and why?
Okay, Greg, do you want to start, maybe? Or...
Well, my knowledge is limited, but it's clear that Chinese researchers have been achieving successes in the laboratory environment and more recently in field experiments, both from terrestrial nodes to another terrestrial node, but also into outer space. But of some interest, I noticed that Chinese researchers involved in the quantum communications are working with a European-based research organization. I can't recall whether it's Belgium or the Netherlands. So it's quite interesting that while China claims all of the credit for quantum communications achievements to itself, it's quite, there's an important element, I guess, which comes from globally available science, but also participation with other with European universities. But that's about the limit of my knowledge. So Michal, I don't know if you could say more decisively or conclusively.
Okay, so basically, if I remember, significant part of the research, especially about the misuse, that is the famous quantum satellite from China, is it was in collaboration also with a researcher from Vienna. So there is a quite strong link between Chinese research and from Austria, where they have pretty good experts in quantum mechanics. So now our tendency a little bit more, I would say that I can see some tendency to lower collaboration with China, but it has not disappeared completely. And for example, in Germany are a lot of the Chinese students. And so in general, I will be a little bit more strict about that, but it's the decision about decision makers, how they, how much precious is for them the national research.
Thank you, Michal. Here's another question, and I think it would be good for both you and Greg to respond to this one as well, because it references Greg's example of cultural challenges when it comes to the adaptation of new technological capabilities. To trust quantum for target recognition and situation awareness requires proven trust in the effectiveness and a willingness of delegate decisions to a quote-unquote black box technology. How would this be handled by armed forces where decision-making is centralized, such as Russia?
Go ahead, Michal.
Okay. Well, question. I think from this point of view, the quantum technology is not so big problem. The big problem here is AI, where even with the classical AI, it seems that we don't fully understand what's going to go inside. So, and here, for example, particularly in NI for these C2 systems, quantum technology or quantum computer only will improve, let's say, the mathematical background behind the AI, but the principles of AI remain the same. And this question is more like about AI itself. So actually, it's pretty big discussion. There are some tendency, okay, it's forbidden. Theoretically, there is some general agreement that, for example, AI for fully autonomous AI weapons are forbidden, but I listened quite nice lecture recently. The boundary is not fragile, but it's very elastic. So everyone can move one side or rather to more autonomous AI. So this question is more about AI. In case of other, for example, quantum optimization, I think we quite clearly see inside. So it's not so big a black box like AI. There I see the biggest big blocks, and therefore, as I mentioned at the end, that development of such technologies, especially for apply for command and control, this should be developed within the national resources, because, as I said, if we don't not always we understand what's going inside AI. So if you want to do some audit verification for before you deploy to your command center, it can be nearly impossible. So that's my point of view.
Greg, do you have anything to add here?
No, let's leave Michal's word on that to be the last.
Okay, well, in that case, I really would like both of you to perhaps, invite both of you to perhaps for some concluding remarks or a statement, anything that you wish to highlight once again, anything particularly that you want our audience to leave this discussion with, one particular point or anything related to what you already said. This would be the opportunity. So maybe we're again going to start with Michal and then move to Greg. And then we're going to conclude our little webinar.
Okay, so first of all, I would like to thanks for this opportunity. So I would like to highlight that the last part, because there are all possible applications. So those points that I believe that in big countries like US, UK, China, they can manage this pretty good. But for smaller countries, as I recommend, you should keep some quantum awareness and monitor quantum technologies. That should be minimum you should do to avoid complete surprising. That's the worst case. You really don't want to have to face some big surprising at the battlefield. So the basic idea is to avoid the surprising, so that you can do at least by knowledge what can be deployed and used against you at the battlefield. And in a better case, if you have enough resources, work on your R&D. So that will be the most important highlight from me. Thank you.
All right. Thank you, Michal. Over to you, Greg.
Well, thanks, Franz, and thanks everybody for coming along to listen to the webinar and participate. I'd like to thank Michal for his presentation. I guess my final thought might be to echo Michal's comments about what do small states do in the face of these very large and daunting scientific revolutions. One of the participants noted in his question before he signed off that maybe the EU should consider setting up a DARPA equivalent. I presume that there isn't one, but not being a Europe scholar, I couldn't say. But this question of how small states adjust to these revolutions is going to be very, very important. And It's interesting to note that Singapore is the 4th ranked state in the world in terms of top ranked, most highly cited papers in the field of quantum enabled sensing and imaging. So I think small states and quantum information science would be a great topic for future work. Thanks, Franz, and thanks again, Michal.
Thank you.
Thank you, Greg. And I apologize that we didn't get a chance to discuss all the questions that were posed over the last the second half of the seminar here. And I also want to thank both you, Michal, and Greg for really an excellent discussion and presentation. I thought it was very insightful, and I already got some really good feedback from people on social media. I was screenshotting some of your slides and sharing them on Twitter already, and that has triggered also an interesting debate. And yes, as a reminder to our audience, just to conclude here, is our discussion here is that the International Institute for Strategic Studies will host its flagship event, the IISS Shangri-La Dialogue, next month on June 4th and 5th in Singapore. And this dialogue is set to bring together leading policymakers as well as thought leaders drawn from across the Asia Pacific, the United States, Europe, and beyond in Singapore to engage in defense diplomacy. And we are particularly excited to announce that US Secretary of Defense Lloyd Austin will take part in this year's dialogue and speak on the subject of advancing the United States Indo-Pacific strategy. And you can go to our website, IISS.org, to find out more about this event. Again, thank you all for your participation. Stay healthy and have a great week.
Thank you, Franz.
Thank you.
Thanks.
Bye.
Thanks.
Thank you, Michal, again. Great discussion.
Thank you.
It was a bit exhausting, no?
Yeah, actually, for me, it was a first really big discussion, because so far my experience are mostly more local with the Czech army. We have some activities and so on. So this was first like a very huge international.
Oh, okay. Yeah. No, I thought it was, a great presentation. I think some excellent questions, and hopefully we can continue the discussion here. It's a fascinating topic.
Sure.
And your paper is really extremely insightful. When we came across this, we just thought that we had to have you and give a talk, and hopefully this is just the beginning of some further collaboration on the subject.
Absolutely. I plan more work on it. As I mentioned, right now I in contact with the Czech army. They have like excellent center for CBRN. So there, for example, need more assessment. What really can be, how well could be used the quantum computer there? If it's a real threat or rather no. So there are more interesting topics, especially in the assessment that there are no answers and many questions.
No, it sounds interesting, definitely. Well, let's keep in touch, and you have my contact details, right? And let's see, maybe we can organize a new workshop again in a couple of months from now. Again, because it's something that we are really looking closely into within our program, and I think so. We're also going to publish this on YouTube and then also our website, and
sure.
We also will we usually get some good feedback, and people are going to reach out to you and so forth about what you said.
Sure. I can send you my presentation in PDF, so you can cut some parts as you mentioned.
Oh, that would be fantastic. Yeah, and as I said,
No
I already shared some stuff on Twitter, and there was some good feedback already on it as well.
Good.
Okay, all right. It was great chatting with you. Have a good day, and thank you again for doing this. We really appreciate it.
Thank you for this opportunity.
Okay, bye.
Okay, bye.